So last time in computer vision, we were talking about some efforts to make RCNN faster. So this basic idea of like the way that we were doing object detection with RCNN was we had our image, we were finding a bunch of windows in that image that might be objects, and then we were running convolutional networks on those little windows to do some classification and to also do bounding box regression. And this takes a long time basically because we have to run each of these little neural networks independently on each of these sub-windows. And so the idea was to come up with a better, more efficient way of doing this that involved basically taking subcrops of the feature map instead of the actual image. And so we went through ROI-align, which is our way of basically taking these crops of the feature map instead of the image, and then once we have something like that, we can run our convolutional network a single time on our basic image, and then use ROI-align or ROI pooling to basically come up with a standard size feature for each of these crops of these different windows in our feature map, and then run those through our classifier and regression network to come up with some bounding boxes and some classification scores. So this was the idea behind faster RCNN, where we're also going to do this proposal box method on top of this feature map. So run our convolutional network, come up with our feature map, run some subnetwork on these features to propose bounding boxes, and then also use our ROI-align or ROI pooling to extract then those features out of our feature map and do some classification, etc., on top of those features. And we talked about COCO, this data set, which is a much larger, sort of expansive data set that also has these segmentation masks for each of these instances. So, every person, for example, has a little mask that's associated with all of the pixels of that person. Same with, sheep and umbrellas and all of the different classes in this data set. So we talked about how faster RCNN performs pretty well on this data set, but why don't we start combining together some of these tasks? So this idea of segmentation and detection, combining them into this idea of instance segmentation. So basically predicting these masks ourselves, similar to how they're sort of set up in the data set. And mask RCNN is basically just this little added structure on top of faster RCNN, where we do the basic faster RCNN. We have our features, we do some bounding box prediction, or we do some region proposals to come up with potential bounding boxes, and then we do our ROI pooling or ROI-align on those features on the feature maps to predict our final classification scores and our bounding box predictions. And with mask RCNN, we're just going to add on an extra little tail here, which will also do our mask predictions for our objects that we might be looking at. And so mask RCNN actually does even better on just the basic COCO detection data set because it has a little bit extra source of information. So it performs a little bit slower, but also can do sort of these added tasks of actually coming up with the segmentation masks of each of these objects instead of just the bounding boxes. The fun thing about the COCO dataset is that it also has captions for each of these images. So there are 5 captions per image, and the idea behind why you might be interested in doing something like captioning is at least one potential argument for why captioning is interesting is like if you just are doing classification or detection, you can get away with basically like pattern matching, right? You can say, okay, there's a person here, or these pixels have a structure similar to pixels before that I've seen that were a person, so I'll just call this a person. But to actually generate, sort of coherent captions for an image, you actually have to really understand what's going on in the image to come up with sort of the right caption, right? So you might, see that there's a horse and there's some people in this image, but to actually, generate a coherent caption, you have to understand that like these people are, using this horse to move some hay around, and they're sitting on top of the hay, and this caption actually isn't great because the horse isn't really carrying the hay, it's like pulling the hay. So maybe, that's an instance of a caption not sort of being perfect, but the idea at least is that captioning is sort of this harder task that maybe requires something more than just pattern recognition, It actually requires some sort of understanding of the world or some deeper kind of analysis or kind of true artificial intelligence. But it's also this interesting task because we have to now model basically both visual information and this linguistic information. And we're going to do both of those tasks basically using neural networks still. So we have a little bit of a domain shift here because images in general are sort of these static things. Sometimes we're playing around with video, and then some of these components come back into play as well. But in general, images are sort of static, whereas language has this new kind of time component. And in particular, we have basically a series or a sequence of data where characters or words are basically appearing in sequence, and you have to kind of read the previous ones to understand what's coming next and be able maybe to refer back to those to do this processing. So, how do we process this time series data using neural networks? What kind of tasks are we going to focus on? Well, sort of the most basic one, and the one that people think a lot about in terms of how we're actually training these neural networks, and kind of a first place to start with is this idea of language modeling. And the idea behind language modeling is you have, some sentence, like a long time ago in a blank far, far away. You have some sentence and you've basically left out some component of that sentence. And the idea with language modeling is, can we read in the sentence either, the words that sort of precede it or some general context around some missing component? And from that context, can we fill in what the missing word is? And in this case, it might be something like galaxy. So there are, a few ways that we could think about doing this. You could take sort of a naive approach, which is your input is just a string. Say it's the string that precedes, the word that we're looking for, and our output is going to be whatever particular word we think comes next in some string, right? So our input would be like a long time ago in a, and our, hopeful output for this network would be galaxy. If we took, sort of this approach, the problem that we run into pretty quickly is that we have this huge expansion in terms of vocabulary, right? So even if we only focused on like a couple thousand common words, if we wanted our input to be some string of words instead of just like a single word, so for example, if you thought about, doing an encoding of all 6-word strings, all of a sudden you have this huge input vector, and that's just looking sort of 6 words back in our input space. Oftentimes the sort of upcoming word in a sentence actually matters, what happened a long time ago in a sort of sentence, in a paragraph, in kind of a body of text. So we want some way of doing this processing such that we can model these longer term dependencies and also don't have, some huge blow up in terms of our input space, in terms of what our input to our neural network looks like. We also just want something that works a little bit more general purpose. If we're only looking at, like the 3,000 most common words, we'll be able to capture a lot of language, but we won't be able to capture a lot of the edge cases that will start popping up as we look at a lot of different text. So what we really want basically is something that is a little more general purpose, isn't kind of like special tuned, for like 6-word input strings or something like that. And the way that we model this with language, oftentimes, or sort of one of the early ways of doing this, was this idea of a recurrent neural network. So recurrent neural networks basically handle sequential data. The idea is that you'll read in one token, which might be like a word or a character at a time, and the network will take in this input, will do some processing on it, will produce potentially some output, and will also update its internal memory or its internal state. And then it will propagate that internal memory or that state forward in time to the next iteration of this network, which is going to be also taking in some input. So every time the hidden layer, or basically the internal state of your recurrent neural network, is being affected both by whatever the input was, but also by whatever the previous layer or the previous internal state was from the network one time step previously. So the idea here is, for example, with our most basic language model task, what we would want to do is read in one word or one character at a time, and then produce as output the next character in a sequence. So if we read the word A, hopefully we would produce long, and then if we read the word A long, hopefully the next word that we would produce as output is time, etc., until we're sort of producing this string in this text that we're kind of reading in. So the idea with training something like this is actually very easy. You find a big corpus of text, you feed in that corpus of text one word or one character, one token at a time, and you train the network to predict whatever the next word or next character is in that text. So just pushing the network towards producing that. And obviously there's some ambiguity in this task, right? Because you could read a long time ago, and there could be a number of different words or phrases that kind of come next in that sequence. So our network over time will get pushed in kind of different directions, and we'll end up, instead of producing sort of a single output, it will produce a probability distribution over possible next words or characters. And then we can do something like sample from that probability distribution, or just take whatever the most likely word or phrase is to be produced next, and use that depending on what our task is. So this is just one particular task that you can think of for how you would start training something like a language model to take in text or produce text, start doing some of this textual processing. So the idea here, again, is we are going to be handling sequential data. We are always reading some input, and then we're also doing some update to our memory at every given time step. So basically we're taking whatever our previous memory was, doing some operation that is kind of the same at every time step. So no matter how far we are along in this sequence, whatever our connections are from our previous time step are going to be the same to make some modification to our memory for the next time step. And so at every time step, we're basically producing some output, potentially depending on what our task is, and also updating the internal state of our recurrent neural network. So there are a number of different kind of things that you can think about. This is like a very general purpose, very basic setup for a recurrent neural network. There are a number of kind of tunable, parameters basically with something like this. One thing you can think of is like, how should we change our memory with respect to our input? What kinds of processing should we do to our input to come up with some changes to our memory? And also how, should the previous state affect what our current memory state is? What kind of processing should we do from the previous state to get to our current state? How do we combine those two factors together to produce some current state? And also, given our input and our current sort of memory state or internal state, how are we going to produce some output for a particular, iteration or round through this network? And there are a few different, ways that people have come up with for actually instantiating, like if this is sort of a general model for a recurrent neural network, there are a few different ways that people have figured out for operations that make sense for this. So one idea is basically just this vanilla recurrent neural network. At every time step, we have some input x sub t. We have our previous memory, h sub t minus 1. And we're going to be producing output y sub t. And the idea here is that our new memory for our hidden state is going to be some weights multiplied by our input x sub t, added on to some weights v multiplied by our previous memory state h sub t minus 1. These are both going to be, some weighted vectors, basically, or these are going to be matrix operations. So they will both produce vectors. We'll add those vectors together and then perform some activation function on top of them. So very similar to basically our fully connected neural networks, but we're just getting input basically from two different sources instead of a single source. But we have some weights and we're multiplying them by our inputs. We're using some activation function. And in this most sort of basic form, we'll just say that our previous memory state h sub, or our current memory state h sub t is also the same as our output y sub t. So our output here will just be whatever our memory state is. And then to get from our input and our previous memory state, all we're doing is multiplying by some weights. And in practice, so yeah, the output here is just the same as whatever our current memory is. So basically we have our weights w, which take our inputs and update the memory, and we have our weights v, which take the previous memory and update our current weights, and we have some activation function phi, which is, again, we're just, because this is in neural network land, we want to apply some nonlinear activation to do some extra processing on top of just sort of a linear model, basically. So this might look something like this, where, if we were using, for example, a tanh function here, if we have our input x sub t here, we are multiplying it by some weights w. We also have our previous memory state flowing in from our previous neural network node. That gets multiplied by some weights v. We add those two vectors together. You can either concatenate them or actually just sort of element-wise add them if they kind of have the same size, depending on what you're interested in doing that can lead to different results. So in practice here, we're just going to append those two things together. We're going to multiply them by some weights w, and then apply our activation function. And our output here is going to be the same as our hidden state, basically, as our memory for our given time step. So are there any questions about kind of this basic vanilla RNN setup? So every time, basically, we have, our previous memory and our current input, and we're sort of generating from scratch some new memory, some new internal state, which is also going to be the output of this network. So one problem with this is this idea of having a long-term dependence in our sequence of data, in the data that we're processing. So at every time step, we're basically completely regenerating our internal state of our network. We're doing this processing where basically we're coming up with a whole new internal memory, sort of from scratch by multiplying our previous weights and input by some weights and then applying some activation function, which in practice means that we're sort of coming up with this internal state from scratch basically every time. And if you have some dependency where some characters or some words that happened a long time ago in your sentence affect sort of how your processing should currently be unfolding, it can be hard to model that because your internal state is basically getting changed, getting rewritten completely every time from scratch. So one idea basically to deal with this, and this is a problem in a lot of basically sequential modeling tasks, is this idea of long-term dependence. One possible way of dealing with this in terms of recurrent networks is instead of basically completely redoing our memory every time, we're going to make some incremental changes to our memory. So basically, instead of kind of rewriting everything from scratch, we will selectively pick and choose which parts of our memory to update. So we'll look at what our memory state looks like. We'll calculate basically a function that decides which parts of memory to keep and which parts of memory to change. And then we'll only basically write to the parts of our memory or the parts of our internal state that this gating function has decided can be overwritten. So there are a few different ways that people do this. One of the most common ones is this idea of GRUs, gated recurrent units, and that's what we'll be talking about. But LSTMs are also very common in sequence modeling. They're basically just a little bit more complex than GRUs, so it's a little bit easier to start with GRUs. Then if you're interested, you can go and look up LSTMs. They're not too much more complicated. And the idea, again, behind this is that this will make our network a little bit more robust, a little bit better at modeling some of these longer-term dependencies because information can flow a little bit more smoothly through the network, through these long sequences of input. So there's a lot going on. GRUs are a lot more complex than kind of our basic vanilla RNNs. So we'll break down basically all of these old pieces. But the idea here is that there are a few steps that basically happen inside of our GRU. The first thing that we're going to do is look at our previous memory and our input and decide what parts of that memory are important. And the idea here is like maybe you were reading a sentence and there were a few different ways that that sentence could go, so you were keeping around a few different parts of your memory. But maybe the new input, maybe the new word that you're reading has sort of changed the interpretation of that sentence, so we can delete basically some of this memory and overwrite it. So we decide which parts of our memory are important and which parts aren't important. The next step is that we're going to calculate some update to our memory. And next we're going to, and so that's basically taking the output of this first step. So after we've decided what part of our memory is important for our current time step, we're going to take that and our input and calculate some update to our memory. Then we're going to decide which parts of our memory we should keep around and which parts we should update. And finally, the output is the old memory that we've sort of kept around, or the old internal state that we've kept, plus the update that we calculated in sort of our second step. So the first part, again, is this figure out what parts of our memory to pay attention to and which parts to ignore. So we're going to come up with this vector r, which is going to be some weights multiplied by our internal state h sub t minus 1, so our previous internal state that's coming in from the previous time step, and our input x sub t. So we have our input x sub t, and we have our previous hidden state h sub t minus 1. We multiply them by some weights w. We have some activation function, and this is going to be a logistic activation function, to come up with this updated, or not updated, but to come up with some vector r here, which will be a probability for every state in our previous time step memory, basically, should we keep around that state or not. So this will be, a bunch of numbers that are between 0 and 1, and we're going to multiply them element-wise by the memory from our previous time step. So basically, we'll be keeping some of this memory, multiplying it by numbers close to 1. We'll be throwing out some of this memory, multiplying it by numbers close to 0. So this r sub t is basically which parts of our memory should we pay attention to for this current time step. The next thing that we're going to do is calculate an update using our input and the important parts of our memory. So we take basically this r sub t, which we just calculated, and do this multiplication with our previous memory. And what's coming through here is just basically the important parts of our memory that we think are important for this current time step. And so we'll use basically this important part of our memory as well as our input to calculate some update using those two components. And our update will be, again, just for all of these components, we're going to be multiplying by some weights with whatever our input is. In this case, our input is going to be the important parts of our previous memory and our input x sub t. And this will calculate h tilde, which is going to be, some updates to our memory. Next, we're going to calculate what parts of our memory to save and what parts to replace. To do this calculation, we're going to use our previous memory, h sub t minus 1, and our inputs. And again, we have some activation function, our logistic activation function, which will give us numbers between 0 and 1. So when we have large numbers here, they're going to get multiplied by whatever our updates are. And those components we will basically be updating. When we have small numbers as the output in this z sub t, those components will not get updated from our h tilde, but we'll use the previous values from our previous memory. So this is basically just calculating a trade-off between what our previous memory state was, h sub t minus 1, versus what these updates h tilde are. So this vector z sub t is basically saying, should we pull updates from this update that we just calculated, or should we use values from our previous memory state, h sub t minus 1? Finally, our output, all we're going to do is basically this weighted sum using our z sub t. So remember, this was what we calculated to decide whether or not we're using our previous memory state or whether we're using these updates that we just calculated, h tilde. And our output is just going to be this weighted sum of our previous memory state and of h tilde, depending on whatever the z sub t is that we calculated. And our output for this unit, as well as our hidden state, are going to be the same. So we're just going to output basically to both sequentially in time and sequentially in terms of our processing, we're going to output the same thing. So our hidden state here is the same as whatever our output is going to be. And that works a little bit different depending on what versions of these you use. So for example, LSTMs do things a little bit differently. But for this, our output and our hidden state are basically going to be the same thing. So sort of complex. There's, again, a lot of stuff going on here. But the idea here is that we have a much cleaner pathway through these units that takes our previous hidden state and potentially brings all of that information through to whatever our next hidden state is. So instead of always going through some multiplications by weights and some activation function, there's actually a direct path that information can take, and in practice often does take, through sequential time steps through this network. And that allows information from much further back in our processing to continue to make it through the network and be useful later on when we're processing things. So in practice, you can kind of think of this sort of like this residual connections that we added in to convolutional neural networks, where the idea was we would have a problem with these very deep networks and getting them to train because gradient wouldn't flow backward through the network very well. So when we added in these residual connections, it gave information basically another path to flow through. This is sort of similar to that, where we want basically some very long-term dependencies to be able to form if they are important. Adding in this extra path for information to flow through the network helps to train the network and also to allow some of that information basically to flow through the network and to have the network basically take into account some of these longer-term dependencies. LSTMs are even a little bit more complicated, where all of a sudden we have multiple sort of paths of hidden states flowing through our network. We have our input. Again, it's very similar in that our input is our input and our previous hidden states are getting transformed. We have some weighted multiplications where we're deciding whether we should pay attention to some piece of our input or whether we should make updates to some piece of our input. We're propagating those things forward. But a lot of the feel, once you actually dive into it a little bit more, is very similar to GRUs, where we have basically these gating functions of deciding whether to use information from the previous time step or whether to use updates that we're calculating. So I'm not going to go into the details here, but again, kind of the important part is that our output, sort of our hidden units or our memory state, has a path that it can take through this network that's sort of unimpeded, that allows some of these longer-term dependencies to be modeled a little bit better by networks that look like this. So this is what the kind of language modeling tasks looks like, and I have some little demos that we can play around with that are trained. Where's my mouse? Just trying to find it. trained using GRUs. So oftentimes you train these kind of tasks on large corpuses of text data. So for example, the one that we're going to look at right now is trained on basically a bunch of news articles that have been scraped from the internet. And this is using a GRU that's modeling the data just one character at a time. So basically it reads in a character or generates a character and then takes that character and feeds it back as input to itself and tries to produce whatever the next character is going to be in a sentence. So we can run this kind of without any seeding information and just have it start kind of generating text on its own. And when you read through the text, it like sort of makes sense, but doesn't really have a lot of semantics to it in that like all of the words are mostly spelled correctly. And there are, things that kind of look like sentence structure, but it doesn't actually like sort of parse when you read the text. It's interesting even just by itself that like using a network that's pretty simple like this, we still can like generate. So it's just, again, sort of spitting out one character at a time, what its predictions are for the next character. And some of these sentences, sort of parse, let's see. She has already described the access to Stephen Grogan, the head of the center's Gene Austin American Teaching Affairs, Lord Tribune, the European company. It talks a lot about companies. It talks a lot about like economics because this is just like scraped from some random set of newspaper data. This is interesting where it like thinks that maybe it's in the middle of a quote. So it ends a quotation and then it says that like this previous portion was said by someone, and then it like describes who that person was, one of the council's board newspaper consultants. So generating textual information, but again, it's just trying to basically generate this one character at a time, which isn't really giving it a lot of ability to, again, one of the hard parts of this is generating these really long-term dependencies. When we're just generating text one character at a time, it's mostly worried about like, can it spell a word correctly? Can it use, sort of a noun where nouns belong and where a verb where verbs belong, etc. But we can also do things like seed this with various little phrases. So for example, we can seed our text generator and say, the first thing that it's going to read is the economic forecast for, and then have it generate text basically based off of that seed. So again, inputting this kind of one character at a time. And then it kind of generates things that sort of, again, make sense with the given context, but it's not sort of this static prediction. We're doing sampling basically based on this probability distribution, so every time we run it, we'll get a little bit of a different result. So the economic forecast for sales and the recovery will start to begin to be at the expense of the Valentine's Day and the something. I don't know where it was going there. Sometimes it sort of veers off course. The economic forecast for the end of Thursday next year, Coral research has surged. I guess Coral research is doing well. The economic forecast for Sunday's presidential nomination. So, it has some ability basically to do some generation that sort of makes sense. And can be useful for a variety of tasks. And once we take this from the character level, and instead of trying to basically predict based on characters, but actually predict based on words, we get better results in terms of generating basically sentences that make a little bit more sense and have a little bit more kind of semantics to them. But the fun thing about these models is we can also just kind of train them on other sources of data. Let's see what else I have this trained on. So this is an example of the same model, just trained on basically song lyrics instead of, you can notice some themes that come about in song lyrics. So some song lyrics instead of the newspaper things that we had before. It's singing about how it had a good day. It has a dream. I like that, sometimes it just gets into these loops where presumably in this corpus there were some repeated elements in songs that happened over and over again. Come on, baby, look in my eyes. You can catch me in the moonlight. It's not a terrible song. I can see the light. I can see you want to shine. So, you can generate some fun stuff with this. This is like, someone had posted online just like all of the lyrics to all of the songs. So it's like some, lyrics website that someone just scraped everything off of. I'm not sure, I can't remember where it actually came from, but it's like, on the order of, well, let's see if I can have it in here. No. This is, a much larger data set than. Let's see how long it takes to load. This file was larger than I thought. Okay, so it has 24 million lines of lyrics. So a lot of lyrics from, all sorts of different artists and genres and stuff. So just like fun things that you can start training some of these language models on, and some little examples of how this works in practice, which on a character level, using GRUs, you can get some interesting results. But once you start moving to word level models or a little bit more complex models, you can start getting things that look much better than just this. So coming back now to our topic, what other kind of tasks can we use? So now we have sort of this basic model that can do some sequential processing, but like language modeling isn't actually that interesting of a task just in and of itself. Sometimes maybe it could be useful to like generate, the next, if you were doing like spell check maybe or something, or trying to help someone like write an email, maybe it would be useful. Google is actually sort of weirdly good at this point. You like start typing in your email and then they say, do you want to say this thing? And then you just hit tab. Or it just has you respond to whole emails by like clicking on a button with a little phrase. But there are other tasks that we might think of. For example, this task of like translation or question answering, which is a slightly different setup, where basically we're given some string of characters or words where we're going to read all of them in first, and then we're going to take basically some internal state or some processing that we've done based on those characters, and then produce some output based on that. So for something like translation, we might take text in one language, process it, and then output some text in another language. There's also this task of question answering where basically you would input some question and then the output would be some string which is the answer to that question. So for something like this, we have a sort of familiar setup that we've seen in the past where we have sort of this encoder-decoder architecture where encoder is basically taking in our stream of textual information and it's producing basically some state or some vector which will be our encoding. We'll take that encoding and we'll feed it in as basically the first step for our decoder, and our decoder will basically take that and process it to produce whatever our output is. So you can have basically a very sort of simple setup that looks like this, that is still using something like GRUs or LSTMs, and basically at every, the way that you would train it is you would feed in some input text. You would sort of ignore whatever the output was for all of these steps, and all you would care about is what the memory vector, what this memory state is that it produced. You would feed that into potentially a different GRU or potentially the same sort of weights and network, and then actually check what the output was and use this decoder to produce some output, and then again backpropagate the information if you're doing something like training. Backpropagate the gradient all the way through this network and update your weights and keep going from there. So if you were doing something like translation or question answering, this is sort of a standard network architecture that you could imagine using. Once we start adding some components of vision in, you can think about doing a task like image captioning. So here what we'll do is, given an image, we'll extract some features using our convolutional neural network. And now our encoder has basically turned into, instead of something like an RNN, our encoder is just, a convolutional neural network. We'll run the image through our CNN. We'll produce some vector, which will be some basically state information. We'll feed that into our decoder, which will be something like an RNN, and have it generate sentences for us. So in this case, our decoder might produce like the dog watches the horse, ... Hopefully, this isn't a real example. And in practice, people have sort of done this and used this kind of setup. It was actually sort of this interesting phenomenon where basically there was 1 year at a language conference where everyone started using RNNs for doing language modeling and started getting some interesting results. And the next year at the Big Vision conference, there were 5 papers that all got submitted that all had basically identical architectures for how to do image captioning. So all of them basically had an encoder that produced some sort of vector here and fed that into like an LSTM or some kind of recurrent neural network, and then all of them sort of produced some output, and they all got like decent results on image captioning. And it was kind of like a little crisis for the conference of like, well, do we accept all of these papers, or like what do we do? All of these things are basically the same paper. They don't really have many distinctions between them, but like it doesn't really make sense to accept some and reject others. So it's just kind of an interesting little side note in the history of computer vision that basically this idea seemed to come up very naturally once this kind of encoder-decoder architecture for recurrent language models sort of existed. It was a very natural next step to take a convolutional neural network and use that as the encoder instead of using some text that you were encoding and using an RNN as the encoder. So a lot of people kind of had this similar idea at the same time. So when you do this in practice, you get some fairly good results. So here are some examples. This is all examples from this. Oh, well, you can't click on it, but in the slides you can go to the website that all of these are taken from. One of the early image captioning papers using recurrent neural networks on top of basically CNN features. A group of people standing around a room with remotes. That's basically true. They're like controllers for a video game. A young boy is holding a baseball bat. A cow standing in the middle of a street. A cat sitting on a toilet seat. Display case filled with different types of donuts, etc. Some of them are not great. I like this one because it's basically the same caption as the previous one. A young boy is holding a baseball bat. A young boy is holding a baseball bat. So that's, obviously I like this one a lot too. A cat is sitting on a couch with a remote control. It like knows that there's an animal here with a remote control, but it just did not get the animal right. A man standing next to a clock on a wall. It clearly sees that there's like a clock here and that there's a man here, but like it again seems like maybe this captioning system is kind of doing some basic pattern matching instead of doing something a little more holistic or something a little more like what humans are doing when we're looking at an image and processing it. Clearly it has certain sort of object classes that it's looking for, like it's really looking for remotes and cats. And baseball bats, etc., and then kind of taking those objects and sticking them into some sort of framework. So it's not always kind of correct in terms of its predictions, and then there are some that kind of just don't make any sense. A woman holding a teddy bear in front of a mirror, like there's not really a teddy bear. I guess this sweater or shirt is sort of fluffy and maybe looks teddy bear-ish, but there's not really a mirror going on in this picture. I like this one a lot because it's clearly using contextual information. It looks sort of like a desert, sort of environment, or maybe like a Western environment where maybe it's seen images in the past where there was a horse in something like this. But it's really hard to kind of figure out in these instances like what's going on. Like a horse is standing in the middle of a road, a toilet seat up in a bathroom. I like this because this is clearly like a bathroom. Like there used to be a toilet here. There just is no longer it like got removed or something. So sort of, interesting examples of failure modes for this, which seem to suggest that kind of what is going on with this image captioning stuff is that it's probably mostly producing captions that exist somewhere in the training data set and doing sort of a nearest neighbor approach where it looks at the image, it finds, the sort of closest caption based on images in the training data set, and then basically produces a very similar caption to that. And actually, a very good paper came out after some of this image captioning hype. A very good paper came out that basically did exactly that. So it took whatever image you were looking at, it looked in the training set and found a similar image in terms of like what objects were present and stuff, and then produced basically one of those captions from the training set, and it got, about equivalent performance to all of these methods that tried to like do something like produce all of this language from scratch. So it turns out that, in practice, actually, it's hard to kind of convince these neural networks to do, any real processing on their own when they can do something a little bit simpler like nearest neighbor, and still get, quote unquote good results. So this image captioning thing, isn't really all it's cracked up to be. And actually one of the reasons is the data set is so large that there are a lot of samples in it of a lot of different sort of scenes and things going on. So nearest neighbor actually tends to perform really well because there aren't kind of a lot of outliers. Most of the images in the test data set are sort of inliers. So if you basically reproduce the same caption from the training data set for an image that looks fairly close, then you'll probably get a good one. There's also an additional kind of problem with doing image captioning as a task computationally, which is that it's really hard to score basically what a good caption is versus a bad caption. So again, this isn't really like a demo, but if we go to the COCO data set, where basically all of these things unfold, and we go to the leaderboard for captioning, we can see basically how these different methods do along a variety of different scoring metrics. And basically the way that you score these things is there are a bunch of automated scores that you can produce, like Meteor score or Blue score, which match basically how close a given sentence is to another given sentence based on sort of what words you use and stuff. And the idea is for every image in our test data set, there are 5 captions associated with it. We'll see which one of those 5 captions your generated sentence matches up with, or we'll do some evaluation against all of those and see basically in some automated way how close your generated caption is to one or to all of the captions that we have generated by humans. So in practice, we have a bunch of different scores for all of these different methods, and you don't really have to worry about what those scores mean. You just have to know that these are sort of in order, so these are like the best methods up at the top. And then if we scroll through for a while, again, these are all sorts of different methods that people have come up with for doing this image captionings. And right down here, I think this is entry like 70 or something, we have humans. So if you ask a human to generate captions for particular images, you can see that they're, way worse than all of these other methods that people have come up with. But that's not actually true, right? What's actually happening is that people have gotten really good at gaming all of these different scoring methods. So if you look at, like Meteor score instead of CIDR, or if you look at Blue score or something, the order actually doesn't really change very much, especially for a lot of these top methods. But you usually have humans falling somewhere. I didn't actually even see them this time around. Okay, here they are, pretty near the bottom. In terms of these automated scoring metrics. And that's mostly just because it's like really hard to tell. It's hard for computers in the first place to do like natural language processing tasks. So it's pretty hard to get a computer to properly sort of evaluate whether or not a caption matches up with other captions in your data set. And in particular for the actual challenge that they did, instead of using automated scoring methods, they just had people go through and say whether or not they thought it was a good caption. And when you have people do this scoring instead of having automated methods, the human captions end up, at like 0.6%, or not 0.6%, 0.63. So this is saying how much do you prefer this caption versus whatever the ground truth caption is. So in this case, the human is sort of fooling the, or you're sort of fooling the human judge 60% of the time, as opposed to these generated methods are only fooling human judges on the order of like a quarter of the time or something. So there's this much larger gap that you see between the human generated caption versus the captions produced by some automated systems. So in practice, it's like, but if you're trying to evaluate basically your own method, it's not really plausible or feasible to like always have humans sort of in the loop doing this evaluation, or kind of doing this judging of whether or not you've basically developed a good caption. So this task in general is just really hard to think about in some method that makes sense, because we don't have an easy way of scoring it, basically. Because there isn't basically an easy way of telling whether or not a caption is any good, it's hard to kind of make progress on it in a way that actually translates to progress according to like some human judges. And it also seems like basically you can use something like nearest neighbor and come up with pretty good results. So like, what's the point of doing all of this anyway? So given that image captioning is, a little bit broken of a task, or has, these various problems with it, people in the vision community basically came up with new tasks to kind of fit into the same conceptual space, where you want to find some task, again, that can't just be sort of solved with pattern recognition, but actually has to use some processing, some sort of higher level processing of what's happening in an image. But instead of something like image captioning, which is hard to score, they really focused on trying to find a task where you could have automated scoring methods that actually, sort of worked well and made sense. So the next kind of attempt at doing something like this was this idea of visual question answering. And the idea here is like, given some image and also some question about that image, can you answer that question? And this still, potentially requires some understanding of what's going on in the image. You have to, both recognize what objects are present, but also what the relationships are between those objects. You have to sort of parse arbitrary language, figure out what the question is answering, and then produce some sort of results to that question. But a key distinction to something like captioning is that now we have a much easier evaluation metric. We can just say, did you get the question right or not? And instead of trying to match up sort of your generated caption with a list of ground truth captions, we can just say, did you get the question right, or did you get it wrong? It's much easier to evaluate. And this is one of the tasks that people have been pushing on sort of more and more, as kind of the one potential direction, or one sort of next step in computer vision for interesting tasks that require a little bit more kind of understanding or a little bit more knowledge than just, sort of the basic tasks like object detection or image classification, etc. So there are some fun demos that we can also look at of visual question answering. Let me pull those over. So we can, try out one of these example images, for example. So if we're using this particular image, we can enter our question, which might be like, what are the people doing? And then it will do some processing, and it'll say they're skiing. It's very confident about that. What color are their jackets? Blue and yellow. That's pretty good. Yellow and blue is also a high confidence answer. Anyone have any questions they want to ask about this image, or some image that they want to ask questions about? And this is a new model, so this is the 2018 winning model, I think, from VQA. What's on the ground? That's easy. I bet it'll get that one. Snow. It's very certain. These are good questions. Winter. So it understands sort of what you're asking, but it just like, well, it's winter. Not sure or can't tell. 2010. It's an interesting one too. We can see what the other kind of example ones are. These ones aren't that interesting. I wonder, yeah, so you can upload your own images. Does anyone have an image that they want to upload? Oh boy. I don't know how you upload it. Maybe you just drag something in. Let me see. Okay. All right. Why is the dog sitting? Floor. Waiting's not bad. Where is the dog? Husky. Not too bad. But that's, just sort of a classification question. The harder questions are, what month is it is interesting. Car. But, daytime. So as you see, these systems can actually do some of the tasks that you'd sort of expect of them, but some things they either kind of fail at the language processing, or it'd be interesting to find, some question or some image that you could ask. Let me just see if there's something in here. I'm trying to find a good image that has, something you could ask more interesting questions about. Here's Hassam presenting a paper. I'll use him. Oh, there we go. What is the person doing? Oh, it had something. I got impatient. Talking. Anyone have any questions or any images they want to ask about? So these question answering systems, work to some extent and get some interesting results. And this is one of the things that people are focused on a little bit more. There are some interesting papers, depending on what the data set is, etc. There's been a lot of work in terms of getting rid of some of the biases and some of the problems with some of the data sets. So there are some papers that came out that were like, can we solve visual question answering without even looking at the image? And it turns out basically a lot of information was kind of leaking through in the textual data. So for example, if in some of the early iterations of these data sets, if you said something like, is there a blank in the image, the answer was almost always yes. So there were like these kind of questions or these setups that didn't make a lot of sense. But more recently, people have been putting a lot of work into balancing out these visual question answering data sets so that the same question appears multiple times, but the answers are sort of randomly distributed between a bunch of different options, and you can't kind of take advantage of patterns in the question as opposed to actually looking at the image. So making these things function a little bit better in terms of actual data sets. Sorry, I lost my next, and now I lost this thing. Lost my little presenter view. And so the final thing that we'll talk about a little bit is with all of these kind of tasks, we still have this problem that long-term dependencies continue to be fairly difficult for these problems. You can think about, for translation or for image captioning, for all of this stuff, for question answering, it still can be hard for information to sort of make its way through this network, through these many rounds of transformations, when we're using something sort of simple like recurrent neural networks to do this processing. So again, this information about one particular word, as it flows through something like a translation model, it has to basically make it through many steps of this process to finally get output as sort of its English translation, for example. So one thing that people use in language a lot, but also has started to come up a lot more in vision and is sort of a general purpose tool, is this idea of attention modeling. And with attention modeling, we're basically going to have the network decide what's important about a given situation or about a given context. And so the network will basically take in a bunch of different information. We'll decide which of that information is important. It's sort of similar to the GRU processing, where the network takes in the previous hidden state and decides which part of that hidden state to sort of pay attention to. So that's one example of this attention mechanism. But as applied to this broader context of something like a language translation problem, the idea is we have our encoder still, which is going to be something like a recurrent neural network, or there are other options for doing this. We have our encoder, which produces a bunch of different internal hidden states. Instead of sort of taking this last memory state or this last internal state as our output and using that as our memory for our decoder, we're actually going to take all of the memory or all of the internal states that we've produced this entire time and sort of stack them up in something that looks like this. And then our decoder, when our decoder is doing its processing, basically at every given step, it will produce some output for what the sort of current word is, for example, but it'll also produce a softmax over our memory context, or sort of all of the memory states of the encoder. It will produce some softmax, and then we'll do basically a weighted sum. So we'll multiply all of the memory states by whatever this attention produced from our previous step in our decoder. We'll do some weighted sum. We'll add up all of those context vectors, and we'll use that as input to our decoder as well. So our decoder will basically be able to take advantage of all of the previous memory states of our encoder, but we'll be able to perform basically its own weighting on those different states to kind of pay attention to what makes sense for it in a given time step. And this actually leads to some interesting results, especially for things like translation, where you can see what input words the network is looking at as we're translating a given sentence. So for example, if we're just translating from French to English, a sentence like I am a student, in French, there are just 3 words, I am student. And so when we sort of visualize what the weight is on of our decoder based on the hidden states of our encoder, we see that sort of the first thing is it's really looking at I for M, it's really looking at the verb. For A, it's kind of balancing out the weight between the verb and student here. And then to produce student, it's sort of only looking at the last word. This gets a little more interesting with longer sentences. So in a number of languages, you switch, I'm not a natural language person, but you switch like the order in which you're sort of using nouns. So instead of like European Economic Area, you say things like the area economic of Europe. So in this case, as our network is translating this sentence from French to English, it's sort of reading through, and most of these words it's sort of paying attention to in order. When it's trying to translate the word agreement or produce the next word in the sentence, it's looking at the word agreement and then the word on. But once it gets to European Economic Area, it's sort of looking in reverse order at those words because it has to produce sort of this flipped version of zona, whatever, I'm not going to try to say it, economic Europe. It has to produce that in sort of this flipped order. And this makes a lot more difference, especially with languages that are a little further apart from each other. So oftentimes there are languages that have sort of drastically different structure in terms of how, what order, nouns and verbs and subjects and objects appear. So instead of basically kind of assuming that like you're always going to be looking at one particular part of the sentence when you're translating that part, using something like an attention model allows the network to basically decide for itself what parts it should pay attention to, where it should be looking in the sentence. And one, just kind of interesting added benefit is that you get to then interrogate the model a little bit and see what part it's looking at, and you can uncover, or just see some of these structures that are already kind of known, but uncover some of that structure based on whatever the task is that you're doing and whatever particular thing you're doing. So on top of this attention idea, the most recent kind of results for doing things like natural language processing and captioning, et cetera, are all based on this idea of transformers. And the idea behind transformers is that we're going to use convolutional networks to process textual data and then use self-attention, so use some attention mechanism to decide which part of the input is actually important to do this processing. And we're not going to go into transformers in this class, but potentially in the deep learning class or potentially just on your own, probably in a natural language processing class too, you'd go into transformers. But they're just like, if you thought GRUs were complicated, transformers are much more complicated than that in terms of how they function. But the basic idea is using this attention mechanism to look across a broad spectrum of your input, decide which of that input is important, and then do some processing and produce some output. And the actual results for attention networks, let me see if I can find some quickly. I can send out a link to about this because I don't have any sort of offhand. But this is if you saw like the GPT-2 stuff where OpenAI came up with a language model that they said was so good that they weren't going to release it because they thought that it would like blow up the world or something. This is that sort of approach of language modeling. So using this attention stuff. So this is one little example or a few little examples that they kind of produced on their website, but the prompt will be something. This is a fun example where they say scientists have discovered some herd of unicorns, and again this is all trained on a big news data set, and so then the model just taking this input produces the rest of this news article about this unicorn. So, the scientists name the population after their distinctive horn, Ovid's unicorn. These four-horned silver-white unicorns were previously unknown to science. Now, after almost 2 centuries, the mystery of what sparked this odd phenomenon is finally solved. It talks about this doctor who's an evolutionary biologist, et cetera, et cetera. And it has a lot of aspects that are actually really interesting in terms of a language model. It's like it takes this theme and maintains that theme throughout the entire piece. So even at the bottom, it's still talking about unicorns, which is, a very long-term dependence that it's kind of carried through in this entire textual stream. It maintains, people that it's talking about. So for most of the article, it's talking about this Dr. Jorge Perez. And then it says, Perez and his friends were astonished, blah, blah, blah. Dr. Perez, however, Perez also pointed out, blah, blah, blah. So it manages to keep a lot of this sort of contextual information around and keep the story very coherent when it's generating these new articles. And this is kind of their initial blog post, but they've released a few of these models, and there are some websites out there too that you can kind of demo generating basically your own news or own text data off of some of these language models. So it's fun to play with a little bit. It's getting, harder to kind of tell the difference between like, did a person write this versus did a, language model write this, which is a little strange of a situation to be in, but that's where we are in terms of language modeling. Yeah, and that's all I have for class for you today. I'll try to find a demo that you can play with for some of these language models because they're fun and sort of creepy to play around with and see how well they do. But yeah, thanks. Next time we'll talk about GANs. Ooh, GANs are fun.